Hi, welcome to the ATAR Notes July lecture series. I'm Isabel and I will be taking you through HSC chemistry. So, let's get started. Ooh, that wasn't what we wanted, but that's okay. So hopefully I can teach you a little bit about HSC chemistry today. A little bit about me. I'm Isabel and I graduated in 2022. I do a Bachelor of Applied Science Exercise Physiology at Sydney Uni, and for the HSC, I did 3-unit maths, English Advanced, Chem, Bio, and Modern, and I ended up getting a Band 6 in all of them. And my ATAR was 99.3. Fun fact, I was considering dropping Chem in Year 12, but ended up keeping it because the main reason I wanted to drop it was I didn't know how to study for it, and I spent a lot of time studying and was not getting the results I wanted. But once I got into the groove of it and figured out what worked best for me and what gave the best results in chemistry specifically, I kept it because it ended up being one of my good subjects. And last but not least, a little bit of non-school facts about me. I like to dance and play touch and go to the beach. So the photos on the side there, one is of me paddleboarding in Hamilton Island, and the other one is of UCID on my walk to my 9 a.m. lecture. So UCID is very pretty. I just thought the building was nice, so I usually like to take photos of that building, the quad, whenever I go past it. So yeah, the game plan for today is to go over all Module 8, so the 3 inquiry questions, and also I'll talk a little bit about like the general vibe of Module 8 because it's a little bit different than the other modules. And then we'll do some revision of the modules 5, 6, and 7. So there's the live chat thing going on the side. If you have any questions, you can just put them in there and I'll do my best to answer them. If I can't answer them, I'll still get an answer to you somehow. But yeah, no question is a silly question in chemistry because chemistry is hard. So if you need any clarification on anything that I've said in this lecture, pop it in the chat. If you have like a practice question, you have questions on, pop it in the live chat. Anything really. Yeah, I'm here to help, so use it. But yeah, that's pretty much what we'll do today. So as for the general vibe of Module 8, I'd say it's one of the harder modules that you have to do in Chem, mostly because of how dense it is and how diverse it is. So you've got skills, you've got memorization, and you've got just some theory content and evaluation that you have to do with the last inquiry question, which is very weird in my opinion. Chemical synthesis is a very strange inquiry question, and I'll talk about that later, but it requires skills in that you have to be able to read graphs. So for organic analysis, you have your IR spec, your mass spec, your NMR, all that stuff, but you also have your colorimetry, calibration curves, all that. Then for memorization, you need to know your solubility rules, your flame test colors, things to do with flow charts in identifying cations and anions. Some questions may even require you to know your colors of certain precipitates. So quite a bit to remember, but don't let it scare you because the good thing about Module 8 is a lot of it is just contextualizing stuff you've already learned in other modules, or just giving more in-depth, giving you more detail into what the other modules are talking about, or how we find out something that we learned in one of the other modules. So really all it takes is some practice and some getting used to, and you're good to go. So we'll start straight away with inorganic substances. So also, before I start with this, if you see me looking here at any point, that's because my monitor is here and that's where the slides are in big letters, and here is the camera. So I will be like, we'll work it out. But yeah, so here is the syllabus for inorganic substances. The main inquiry question is, how are the ions present in the environment identified and measured? So basically, you can break this down into 3 parts. The first part is monitoring the environment. This one's a really easy one. You just have to be able to articulate why we need to monitor the environment. Then the second one is qualitative investigations. This is figuring out what cation is it, what anion is it, based on primarily two things, the flame test and precipitation, but also complexation, which is a little bit tricky, but we'll get to that later. And then the last part is quantitative investigations, which is your gravimetric analysis, your precipitation titrations, colorimetry, UV vis spec, and AAS. So quite a lot to cover in this first inquiry question, but as you go through it, you'll see that a lot of it is stuff that you've heard of before, or just pretty self-explanatory stuff. So an example of the self-explanatory stuff is monitoring the environment. So this one is a pretty easy dot point to check off because it's a lot of common sense. So we need to monitor the environment because the environment is very important to both human health, also the health of different parts of our ecosystem. So for example, waterways, we need to make sure that they are not getting bombarded with toxic chemicals from nearby factories. We need to make sure that that water is still drinkable for resident wildlife and still usable for watering the crops that are grown in those nearby areas. So that's why it's important to monitor toxin levels in water. And yeah, just to prevent a buildup of toxic waste. So an example is lead. There was an issue in Japan where there was lead in waterways, got into the fish, and then when cats ate the fish, it caused the cats to have symptoms of lead poisoning because there was lead in the system of the fish. So it's just a cycle, basically. It interrupts how our ecosystems work. So it's really important that we prevent that buildup of toxic waste in the first place. And how we do that is by monitoring the environment. And then the other main example is the atmosphere. Again, it's pretty common sense because the atmosphere is the air we breathe, and we don't want the air that we breathe to be toxic for obvious reasons. But buildup of toxic chemicals not only can make it difficult to breathe, but can also cause acid rain, which has a bunch of other issues, not only for humans, but for, again, environments and plant and animal life. So it's very important that we monitor the atmosphere, particularly carbon monoxide and lead. So lead from leaded petrol, burning of leaded petrol can send lead particles into the atmosphere, and when that happens, if there's a buildup of lead in the atmosphere, we could get lead poisoning from just breathing, and we don't want that to happen. Lead poisoning is not fun for anyone, so that's why we need to monitor the environment. Basically, this whole dot point is just you being able to go, if we put toxins in vital sources of life, so water is very key to life, air is very key to life. If we put waste in that and put toxins in that, it's obviously going to have very negative impacts. So that's basically all you need to be able to say on this one. Another thing that comes under this is eutrophication. This one is a process that is really good to remember, just because it's very relevant and very easy to remember. It's while it is memorization, it does follow a very, very logical process that makes it super easy to remember. So first, what happens is that fertilizer runs off into waterways, and the nutrients from this promote algal bloom. That is the green stuff that is on top of the water. And then what happens is, you can see in that photo that the green stuff is quite dense, quite thick. So basically, we need to make sure that that doesn't happen, because if that does happen, then that blocks the sunlight from going into the water, and it prevents the plant matter in the water from being able to photosynthesize. When it's unable to photosynthesize, that plant matter dies and the decay uses up oxygen. The other thing about photosynthesis not occurring is that when photosynthesis doesn't occur, oxygen isn't being produced in the water, which means that there's less oxygen in the water from both decay and lack of photosynthesis, and therefore a lack of oxygen for the animal life in there, which causes like the fish to die, any other animal life in there to die. So it basically ruins the whole balance of that ecosystem. So it's super important that we monitor fertilizer levels, not just toxic chemicals in our environment. So that's basically the first dot point of the syllabus done. Moving on to the qualitative investigations, identifying cations and anions. We'll start with cations. So there are 3 ways that you can identify cations. It's the flame test, the precipitation reactions, and also complexation. For flame tests, really all it is being able to memorize the colors that go with what cation. So on the left, we have a list of the cations we're supposed to know, and so supposed to be able to identify. And then on the right, we've got some of the main colors. So barium is apple green, calcium is brick red, lead is white. Lead, I don't know if you've done a flame test before, you should have done one, but just like a side note about lead, if you're using an example in your exams, you should never use lead flame test as an example, because you should not be doing that in a classroom setting, because lead is toxic, as we know, and if we're spraying around lead or having lead just out in the open, it's not good. So when we're using flame tests as an example, we should use something like copper or calcium or barium or iron, not lead. Anyway, that's a side note. Copper has a blue-green flame, iron is a yellow flame. So whether you got a solid, put it on a little bit of one of those loops and then put it over the flame to get the color, or you sprayed a solution of it through a flame to get the color. In both ways, lead should not be used. The rest, it's fine to use them as an example, but basically just know those colors, know those ions, and that's basically all I could tell you about the flame tests. But yeah, just know the colors. That's really all that you can do for that. So for precipitation, you need to know your solubility rules. So solubility rules, they come up everywhere in a whole bunch of questions. So it's very important that you know them, and how I remember them and how I think a lot of schools teach you to remember them, it's NAG-SAG. So NAG-SAG is for nitrates, ammonia, group 1, sulfates, acetates, and group 7. And then for sulfates, they're all soluble except for calcium, strontium, and barium. So how my teacher told us was castrobar, however you want to say it, that's for sulfates. Those are the exceptions for sulfates. And then PMS for the exceptions for group 7. So group 7, they're all soluble except for when they're with PMS, which is lead for PB, magnesium, and silver. It's Ag, but S for silver. So in summary, cations, all group 1 is soluble, castrobar are not soluble with sulfate, and PMS are not soluble with group 7. So if you just know the solubility rules and know their exceptions, precipitation is really, really easy, and it should come just naturally. Once you do lots of questions, you'll know the common ones that they like to bring up. So a lot of the time they like to bring up barium sulfate. I don't know why, but barium sulfate comes up a lot. And yeah, so just the more you practice the questions, the easier it gets. So we'll do a little bit of practice. So predicting whether these will be soluble, following the solubility rules. So silver chloride is a group 7. So they are all soluble except for when with lead, magnesium, or silver. Since this is silver chloride is insoluble, so it would form a precipitate. Barium sulfate, I kind of said this before, but sulfates are all soluble except for when they're with calcium, strontium, or barium. This is with barium, so it's insoluble and will form a precipitate. calcium chloride. This is a little bit tricky because if you remember the exceptions, but you get them mixed around, you might think that calcium, when with group 7, produces a precipitate, but it does not. Calcium produces a precipitate with sulfate, but not group 7, so calcium chloride is soluble. Lead chloride, on the other hand, is insoluble because lead is the P in PMS that is the exceptions to group 7. So that's that. And then iron nitrate, iron 3 nitrate. Nitrates are all soluble, no exceptions, therefore iron nitrate is soluble, no precipitate. So that was a little bit of the thinking process when you go through it. So just go through your NAGSAG. If it helps, you can, whenever you have a precipitation kind of question, just write NAGSAG somewhere. It will probably jolt your memory and help you remember what your solubility rules are. But yeah, just know them and you're all set, and they'll be pretty easy from then on. So complexation is another way to identify a cation, and most of the time it comes with a very drastic change in color, and that's what identifies whether it's there or not. So for example, if you have a solution of iron, and let's say it's pale yellow, which it usually is, you have a solution of iron and then you add your thiocyanate, complexation reaction occurs, and this causes it to go blood red because of complexation. So that's an example that you should have seen in module 5, iron thiocyanate, and that complex. But basically complexation as a whole, it's when two substances react to form a complex. And in my head, how I remember it is there's an X in complexation, so it kind of looks like an X. So it's like a one central one with like an X around it. That's how I remember it. Sometimes there's like 6 or 8, not 4, around the cation, so it doesn't look like an X, but usually there is. So there's some sort of like a cross over like a central cation. So that's just how I remembered it. It's a bit silly, but you know, whatever gets you to remember chemistry, it works. So yeah, you don't see this a lot in the HSC, but if it were to come up, most of the time it would include water, ammonium, or hydroxide. Or, like the example I said earlier, iron thiocyanate, because that's something you should have encountered in the past modules. So it goes from that pale yellow, clearish color to blood red. And that's how you know that complexation has occurred, and that's how you know that there are iron ions in the solution. So that's one way of identifying it. So now to anions. Precipitation follows the same things as the cations in terms of the solubility rules. You just go through the solubility rules and you should have some type of answer to what anion it is. But some other bits and pieces to remember are that carbonates and phosphates are insoluble, and hydroxide is insoluble, but with the exception of calcium and barium, which are sparingly soluble. So that's the only extra piece of information you need to know other than the solubility rules. Everything else you can figure out with just the solubility rules. So another thing is, we'll see this in another slide, but if you have a carbonate ion, it will react with acid, because if you remember from year 11, acid carbonate reactions produce carbon dioxide. So what will happen is, if you have a carbonate, a test to figure out if it's a carbonate is you add an acid to it and it forms bubbles, and those bubbles are carbon dioxide. But we'll get to that. So for flowcharts, a lot of questions when it comes to identifying ions, it requires thinking like a flowchart. So it's like the process of elimination, basically. So you start with something, and then if it does this, so let's say you start with all the cations in a mix and you add chloride, then you can have a precipitate form with lead or silver. Then, when you're choosing between those two, what you can do is put the precipitate under UV light, and then silver will decompose. So that if it doesn't decompose, you know it's lead. If it does decompose, you'll know it was silver. So that kind of thing. If you add sulfate, barium, and calcium precipitate, and then you can distinguish them based on the flame test colors. So it's like you narrow it down and you narrow it further and further down using a bunch of different tests until you have only one possible ion. And sometimes you'll be required to draw up a flowchart of how you'll find that final ion. So it's good to know all of the options that you have. So if you add hydroxide, magnesium, iron, and copper form a precipitate. And this is where it's important to know the colors of the precipitates. Most of the time, it's similar to either their flame test colors or it's very distinct. Most of the time in the HSC, if you do need to know the color of the precipitate, it'll never be like a white precipitate. Well, it could be, but they'll give you enough information so you don't have to just know the color of the precipitate, if you know what I mean. So for example, lead iodide is a bright yellow color. That bright yellow color should immediately let you know that it's lead iodide. But if it's magnesium hydroxide, which is white, barium sulfate and calcium sulfate are also white. So they wouldn't give you something where there's lots of options. They'll give you something where there's only one option. So it's just something to think about when you're stuck with a question. There's only one answer, really, so you just have to keep doing stuff to figure out what it is. So, for example, if you have 3 white precipitates, maybe all of them give a different color in the flame test, stick them in a flame, and that'll give you your answer. So it's just those kinds of flowchart questions. Anyway, back to the slides. Magnesium hydroxide is white, copper hydroxide is blue-green, and iron hydroxide is white but oxidizes to green, and iron 3 hydroxide is yellow-red. So they all have different colors except for the 2 white ones, but one oxidizes to green. So in that situation, you'd oxidize it. If it turns green, you'll know that it was iron 2 hydroxide. If it doesn't, you'll know it's magnesium hydroxide. So a bunch of different options there. And the same with anions. As I said before, the thing with acid carbonate reactions produces CO2 bubbles. If you react it with copper, a blue precipitate will form with phosphate, and a blue-green precipitate will form with hydroxide. And if you can't tell the difference between blue and blue-green, I get it, because it is a little bit hard to tell. But another thing is, if you react an acid with a hydroxide, it'll be more vigorous than an acid with a phosphate. So you can just see for yourself. For barium, it'll form a white precipitate with sulfate, and lead, as I said before, a yellow precipitate with iodide, white precipitate with chloride or bromide. And then, if you're choosing between chloride or bromide, there's a cream-colored precipitate when added to silver when it's bromide, and then silver chloride is white. So again, you just need to just keep adding stuff until you narrow it down to one last one. So we'll do a couple of questions. This first one, if we read it, the student finds an unlabeled beaker. It's left over from a previous prac, so they deduce it must possess carbonate, sulfate, or chloride. They add nitric acid, they don't observe bubbles, then they add barium nitrate, and they observe a white precipitate. So, if we use the logic of process of elimination, it cannot be carbonate, because if it was carbonate, it would react with the nitric acid to form bubbles. Then that leaves you with either sulfate or chloride. That's when you go to your solubility rules, because it says that a white precipitate was formed. That white precipitate has to be either barium sulfate or barium chloride. If you remember from the solubility rules, you'll know that barium chloride is soluble because it's a group 7, and barium is not one of the exceptions. So it has to be a sulfate anion. There you go. That's how you figure out a question like that. So I eliminated it until there was only one left. That's how you should approach those questions. For this question, it's really just knowing your solubility rules. It looks a bit complicated, but really all you have to look is at the end of step 3. So iron chloride is added to sodium hydroxide to form a brown precipitate. So if we look at the reaction, iron chloride plus sodium hydroxide will make iron hydroxide and sodium chloride. So we know sodium chloride is a group 7 anion and a group 1, so it's soluble. And we know that iron hydroxide is a hydroxide, which is insoluble. And iron is not one of those exceptions to hydroxides being insoluble, so therefore the brown precipitate has to be iron hydroxide. So again, just the process of elimination and using those solubility rules to find that final answer. But yeah, so that's that. So that finishes up the qualitative investigations, and now we're onto the quantitative investigations. So this is not just identifying, but being able to measure. And for gravimetric analysis and precipitation titrations, I'm not going to talk about them much because gravimetric analysis you should have done in year 11, and precipitation titrations follows the exact same process in calculations as normal titrations. In precipitation titrations, there's a bunch of different methods that you can use to do a precipitation titration, but generally the endpoint is where there's no more precipitate being formed. So when you approach these questions, it's really important that you're good with basic moles calculations, because that's where most people would go wrong in this situation. Not knowing your moles and not being careful of balancing your chemical equation at the beginning to make sure that all your ratios are correct. I think the most important thing in chemistry is writing down the equation to start off with, because that can help you avoid so many mistakes along the way if you have a good balanced equation at the beginning. So yeah, gravimetric analysis is determination of an analyte based on mass, and then precipitation titration is based on when that endpoint is reached. So just know your moles, just be very careful with those moles when you do the calculations, otherwise they're very simple. And it's something you've done before, so I won't go over that. So another way that you can measure is colorimetry, and the main way that you will see this come up in the HSC or in your trials is as a calibration curve. Either you having to draw one and then look at the absorbance for a sample, or just find out the find out the concentration based on the absorbance. There's lots of different ways, but it almost always ends up with you reading a calibration curve. So I'll talk about that more in a second, but just some theory behind it. It's based on how intense the color is. So some more theory behind it is just that when energy is added to the atom, it excites the electrons, and then when it goes back into its ground state, it emits a photon, and that's color. And when it emits that, it means when it emits more of that, it basically means that there was a higher concentration. So the more energy it emits, the more concentration it has, and that can help us figure out what the concentration of something is. So basically, that's the theory behind it. I'll go straight into how it will come up in the HSC, and it's just a calibration curve. So key things to a calibration curve is that it needs to be precise when you're doing when you're making like the standard curve. So you use known concentrations, find out their absorbance, and then plot it, and then you should get a pretty straight line if you're super precise. And when it's really straight, you can have an equation for the line if it's there in your question. That's really good because it makes it really easy to find out concentrations based on absorbance. But if not, the standard way to approach this is you get your absorbance. Let's say it's 0.3. You just you draw a line across until it hits the line, and then you draw a line down, and it hits the line again, and then you read off the concentration. So basically, that's all there is to colorimetry, just being able to read off that graph or use the equation of the line to find out your absorbance or your concentration. That's really all you have to do for colorimetry. Now, UV Vis spec is a little bit tricky. It doesn't come up much. It did end up coming up into my HSC, which was quite unexpected because I was told by everyone, oh, it probably won't come up, but it will. It will if you're not prepared, so be prepared for it, just in case. It's very similar to colorimetry, but how it works is that it measures the wavelengths of light absorbed by a certain compound, and this corresponds to certain bonds. And all that information is on your data sheet, the bond stuff, but how it came up into my HSC was this question here. So it says which wavelength would be appropriate to determine the concentration of Q in a mixture of two solutions. Basically what you're looking for is a place where the solution Q has a high absorbance and solution P has a low absorbance. The two areas where this happens are here and here. So 475 and 630, which both happen to be options in the multiple choice. Basically what it comes down to is that we want 630. That's the correct answer. D is the correct answer because you'll see that P does not have any absorbance at that wavelength, which means that we know for sure that everything being absorbed at that wavelength is being absorbed by Q, which means the concentration that we will calculate will be the concentration of just Q, nothing else. If we do it over at 475, some of it is being absorbed by P, so we'll have a number that is much higher than the actual concentration because we think that the little bit that's being absorbed by P is actually being absorbed by Q. So that's why we need it to be 0 for P and then high for Q. So 630 D, that's the answer to that question. So another part of UV Vis spec is the Beer-Lambert law. This is a little bit of a weird part of the syllabus, I'd say. It doesn't come up often, again, but it's still worth knowing. The equation is on your formula sheet, and it looks exactly like that here. This is just on the top of your formula sheet, and what you need to do is just plug in the numbers, basically. So knowing what everything stands for, you got your IO, which is the initial light intensity, and the I is the final light intensity. So that intensity is after a little bit's been absorbed by whatever is in the cuvette. Then the funky E looking thing, I don't know what it's called, but it's the molar absorptivity, and the L is the length of the cuvette, and C is the concentration of the solution. So you just need to be able to plug in the numbers, and it's really easy from there. So an example, a red solution has a molar absorptivity of 2 liters per mole centimeters. If a light passes through 4 centimeter wide cuvette and has an absorption of 6, what is the concentration? So yeah, you'll have to work backwards because in this case you have the absorbance and you want to find out the concentration. So here's the solution. Absorbance is basically the 2 times the 4 times the mystery concentration, and that absorbance is equal to 6. Then 6 on 8 simplifies to 0.75, so the concentration is 0.75 moles. So that's basically how you use the Beer-Lambert law. You can also use it with the light intensity stuff, but I didn't have a practice question for that. So just know that if we go back, just know that the incident light is what goes on top and the transmitted light goes below it. So that's really all you need to know. Yeah, so we'll move on to AAS, so atomic absorption spectroscopy. And this is similar to the other methods that we've been discussing already, colorimetry and UV Vis spec. And it's determining the concentration of a compound based on the light absorbed or emitted, and it's very useful for trace elements, very small concentrations. So use it a lot for like figuring out if there's too much of toxic chemicals in the environment, because usually it's very small concentrations that make a very big impact in the environment. So the steps that it involves are, first off, the sample is vaporized, and then once it's vaporized, it has a cathode lamp light shone into it, and this goes to a detector, and this determines the amount of light absorbed by that vaporized substance. Then after this, it goes into a computer, which does all the tricky stuff. It just compares the absorbed light with the standard curve, and then it allows the concentrations of ions to be determined. So really the main steps is, first, it being vaporized, and then second, the light being shone through it, and then third, the detector. So those are the key things that you should remember for the process of AAS. That's what it looks like. So you've got the hollow cathode lamp, you've got the vaporized substance, you've got the monochromator and the detector, and then the computer, which does all the data processing. Okay, and then some examples are, or some examples of where it's been used is in South Australia to identify regions that were lacking in cobalt. And yeah, so basically it's just used to find and monitor trace elements, very small concentrations. If the concentration is too small, it won't show up, but like this can do pretty small concentrations. So it's good for finding those small concentrations. An example of putting all of this together is this question. So this is one of the sample HSC questions from NASA, and it uses complexation as its main thing, I guess. So if you look at the question, I'm going to read it, I guess, because I don't know. A colorimeter was used to calculate the percentage of iron. Tablet was dissolved and oxidized. That's the reaction. The resulting solution was made up to 200 milliliters with distilled water. Absorbance was 0.6105. That's a calibration curve. How much iron was in that tablet? Now, this would have sent me into a panic if I was in the HSC, because there is so much information being told to me. I've got some reaction that looks like complexation. I have 200 milliliters. I have an absorption. I have how much gram the tablet was originally. And then I've got this calibration curve. It's quite overwhelming, all of the stuff that's on the screen. But if you take it step by step, it's actually quite simple to figure out what's happening here. So the first thing that you would need to do is check that the equation is balanced. It is balanced, so you're all good to keep moving on to the next step, which is to ignore the 200 milliliters with distilled water for now. Just because that's something that comes up later. If you worry about it now, you're going to forget the main part of this, which is reading that calibration curve. So they were kind enough to give an equation for the calibration curve, and that is y equals 0.0111x. So if you use the absorbance, which is 0.6105, and you multiply and you divide that by 0.0111, you'll find that the concentration is 55. So it's 55, I want to say micromoles. I think that's, yeah, micromoles. So 55 micromoles, and we want it to go into moles just because it's so much easier to deal with moles than it is micromoles. So then what you need to do is convert it to moles, and how you do that is move the decimal place back, and then once you have it in moles, you want to put it into the 200 milliliters that it's in. So it's micromoles per liter originally, and then once we convert it to moles per liter, we want to find out the actual number of moles. And how we do that is by ignoring that 200 milliliters and using that to find out the number of moles. So we times it by 0.2, and then once that happens, you can multiply it by the molar mass of iron, and that should give you an answer. So, it's a little bit blurry, but we'll deal. That was basically how I did it. I talked through it all just then, but written down, it kind of makes more sense. But yeah, so the important parts to remember for this type of question when there's so much information is keep in the back of your mind how many milliliters it was in. So in this one, it was in 200 milliliters. You don't want to be going on with the question assuming that it's in 1 liter when it's in something smaller, because that can lead to a completely different answer. So don't disregard that, but don't worry about it straight away. You'll see that I only used that in the second part. If I used it right in the first part, I would have gotten confused. Something would have gone wrong. So it's very important that you deal with the absorbance first, and then you deal with the moles. Just like I did here. So the answer in the end happened to be, what was the option? C. It happened to be C. So for those types of questions, just be really careful with your moles. And if you're doing any type of making it from millimoles to moles or micromoles to moles, just be really careful with your decimal places there. But yeah, that was one of the sample questions, and once you go through it, it's actually much easier than it looks. So, some more practice questions before I move on to the next question. Basically, first, which of the following could not be used to determine the concentration of an ion? The answer is flame test, because flame test does not tell you anything about the concentration of an ion. It only tells you what ion it is. So that is the flame test. Question 2, which of the following will form a precipitate with sulfate? If we look at all of them, only one of them is from the Castro-Bear exception, and that is barium. Like I said earlier, barium sulfate is one that they love. They love using barium sulfate. Who knows why? But yeah, so barium, C. And then for question 3, which of the following might be a useful way to check if iron 3 is in a solution? And this goes back to complexation. So if you remember my example before, iron thiocyanate, that complex, that goes from a pale yellow solution to a blood red one, and therefore option F, it's not A, B, C, or D apparently, it's option F. Option F, add thiocyanate, is the correct answer for that question. So that's basically all of that first inquiry question. And now we'll move on to the second inquiry question, which is organic substances. And this is my favorite part of the whole, like, probably the whole of HSC chemistry. This has some of my favorite stuff in it, so get excited, but not too excited because it actually is kind of hard, but we'll see. So this is the syllabus. The inquiry question is, how's information about the reactivity and structure of organic compounds obtained? And it looks smaller than the first one, but this is a lot of skills-based stuff. So we'll just go through it quite thoroughly, so you get used to the kinds of questions, because this is quite new, but I can almost guarantee you that there will be a question from this section in your HSC or your trial. Like, it's always worth lots of marks, and it's really good at distinguishing people who just learned everything and people who actually understand what's happening, because all the questions could be so diverse, could be so different. It's the skills that really matter in this part of the syllabus. So I'll go through that some more with you now. So first, qualitative tests of organic compounds. This is just how to determine different functional groups and different bonds. So the carbon-carbon double bond, it's the bromine test. We know this one. It will decolorize bromine water. That's the main one you need to remember. There's also this other test where the addition of permanganate, potassium permanganate, potassium permanganate triggers a change in color. Then you've got your hydroxyl groups, which are like alcohols, and you have your active metal test. So if you add it to active metals, it will trigger the production of gas. That's a really easy one to remember. Another one that some people like to mention with hydroxyl groups is adding like acidified permanganate or dichromate and seeing the color change, because alcohols oxidize obviously, and this will change the color. But this doesn't really work because other organic compounds can oxidize as well. So if you remember from your organic chemistry, aldehydes can also oxidize. So it'll have a color change if it's an aldehyde, but also if it's an alcohol. So like that's not one of the best tests. That's why it's not written here. Yeah, and then you also have that other test, which is adding steric ammonium nitrate to change color. And then you've got your carboxylic acid tests, and this is all basically stuff that you could do with a normal acid, so litmus paper, and also sodium hydrogen carbonate testing, which produces carbon dioxide bubbles. And then also ester test, so if added to an alcohol under reflux conditions, if it produces an ester, which is usually associated with like a fruity kind of smell, if that happens, then it's a carboxylic acid. So carboxylic acids, you can basically test its presence, I guess, with any acid test. So litmus, sodium hydrogen carbonate. That's basically it for that part. Now we're going on to my favorite part of the syllabus. So this is structural analysis techniques. So there's a little bit of theory behind this, but the most important thing I want you to get away from this lecture series is that it's the skills that matter. You could remember every single, there's no possible way you could know what they're going to ask you about. Like, it could be any organic compound ever that they're going to ask you about. And if you don't know how to interpret the graphs, there's no way for you to know what that organic compound is. So that's why it's really important to really hone in your skills in this section. So we'll look at 4 main things: mass spec, infrared spec, NMR, and then UV vis spec. But we'll mostly focus on the first 3 because those are the 3 that come up most often in these types of questions. So let's get into it. Mass spec involves turning a compound into an ion. What happens is an electron beams past through and it makes it into a bunch of smaller charged fragments, and these are then passed through a kind of magnetic field, and when they move through that magnetic field, they go in certain directions, and that helps determine their mass. So if it's a lighter mass, that magnetic field would move it more because it's lighter. If it's a more heavier mass, that magnetic field will move it less because it's heavier. So knowing the way that an organic compound breaks apart can help us figure out the different fragments and can help us figure out what compound is represented in one of these graphs. So I'll give you an example. This is what they look like. It looks like a bunch of lines around, and there are lots of different peaks and that kind of stuff. But the main things to remember are that the one furthest to the right, the furthest to the right peak, that would be our molar mass. So the largest fragment size is our molar mass, because yeah, that's just how mass spec works. Then the other lines are different fragments. So this one is the mass spec of pentane. So that 43, that really high peak there, that's 43. That would be a propyl group. So if you look down here, I did the maths for you, drew it out. That's what the group fragment will be. And then you also have the 29 peak, which will be a ethyl group. So those are 2 ones that come up really often in mass spec, just because a lot of compounds would have a group that's like an ethyl group or a propyl group. So knowing that 29 and 43 mean those things, sometimes they can mean something else if it adds up like that, but most of the time it will mean an ethyl and a propyl group. So just remember those numbers. They can be super handy when trying to figure out like the organization of an organic molecule. Like, you'll know straight away that 43 means that there's 3 carbons, a proper group, and you'll be able to figure out, like, it's super good to remember. But yeah, that's mass spec basically. Here's a practice question. So as I said before, the furthest one, which is that 88 over there, that is our molar mass. So that's the first thing you should look at when you look at a mass spec thing. You want to look at that molar mass, and here, when you look at that molar mass, you can rule out most of the options. Then the next thing that you need to look out for is the fragments. So that 60 is very important. You need to find out what that 60 means. So if we go to our little calculator and do a little bit of maths, so yeah, so when you go to your calculator, do a little bit of maths, you'll find out what all of those fragments mean. But basically, how I did this was 88 is either B or D, and D is iron sulfide. It cannot be mass spec'd because it doesn't fragment like that, so it has to be B. That's literally the way I did it. It's pretty easy to eliminate. So I eliminated A and C because it didn't add up to 88, and then iron sulfide is just impossible, so it has to be B. So that was like a really quick way to do it, but a lot of the time there will be like an obvious answer, and if not, then look at the fragments, look at what that 60 means, or that 27, or that 41. But yeah, that's all I really have to say about mass spec. Most of the time when you look at mass spec, you will be looking for that molar mass, and that can help a lot with determining how many carbons there are in a molecule. So yeah, mass spec is often paired with IR spec. IR spec is for functional groups, determining what functional groups there are. So they store energy in the way that bonds vibrate, and when the infrared light strikes a molecule, it can be absorbed by these bonds, and it can cause them to move in a certain way before being re-emitted. And it's a similar idea to colorimetry, but basically we measure the wavelength of the lights that are absorbed, and this tells us what bonds were absorbing those. Yeah, what bonds are present. So I'll show you what it looks like. So on the left, that's basically what you get in your data sheet. So it has the wavelengths for different bonds, and then you'll be shown a graph that looks like this. So we call them peaks, those dips, even though when you think of a peak, you think of it going up and down. You call these peaks still, even though they're more like troughs. But yeah, an important thing to note is past 1,500, so this stuff here, that's called the fingerprint region, and we usually ignore the fingerprint region except for when there is a very distinct peak that just has to be mentioned. So most of the time that would be a CO bond. So when you see that distinct peak in the fingerprint region, that's the only time we can really read from it. All the other times we just ignore the fingerprint region and we focus more on the more defined peaks on the left hand side. So if we look at this what's it called? This IR spec here, we have that broad one, that broad peak here, and this looks like it's an alcohol. So it goes from 3230 to 3550. It sits on that range, and it's pretty broad, so I'd say that that's an alcohol. Then if we look at the one next to it, around 3000, oh, it's probably going to be a CH bond because it sits in that range. So that means we have an alcohol, just a normal alcohol somewhere. We ignore the fingerprint region because then there's no big peak or anything happening on that side. it's just small peaks that are quite undefined. So we ignore that and we just take the information from this side. So the fact that there's probably an alcohol hydroxyl group and that there's CH bonds. So this tells us what functional groups there are, but it doesn't really give us too much information on the position of said functional groups, or how many carbons there are, how many bonds that are alcohol, like how many alcohol groups there are, how many bonds there are. All of that information is not here. So we always need to use it with something else. So with mass spec, if we have it with mass spec, we could maybe find out how many carbons there are in this alcohol molecule and figure it out from there. Or if we have it with HNMR and CNMR, we can find out exactly the position of the hydroxyl group and the exact number of hydrogens, carbons, all that stuff. So you never just look at an IR spec on its own. So I started talking about NMR, which is nuclear magnetic resonance, and this is a little bit tricky theory-wise, but basically all you need to know is that it has something to do with how the nucleus spins. So if it's spinning one way and then it switches to spin another way, we can gain information on like what type of nucleus it is. That's a really simplified way of saying it, but basically because of NMR, whether it's CNMR or HNMR, which are the two main ones that you'll get in the HSC, when it comes to it, all that it comes down to really is that it gives us a diagram that can tell us exactly where everything is. And I'll go through how to read those diagrams in a second, but you can, like, these are the make or break diagrams. If you have a question and it has mass spec, IR, and NMR, you could just read the NMR and you could probably figure it out with a little bit of help from the functional groups IR information, but like NMR is just very comprehensive with the information that it gives you. So it's very important that you know how to read these, and I will go over that now. So HNMR, the trickiest part of Module A, and it's tricky because it has this thing called splitting, and I'll get to that later. But so first things first, when you look at an HNMR diagram, you want to count how many peaks there are. And by peaks, I mean like the clusters of peaks. You don't want to count the individual peaks just yet, just want to count those clusters. So here you have 3 clusters, ignoring that TMS at the end. And those 3 clusters means that there are 3 unique hydrogen environments. So each cluster corresponds with a unique hydrogen environment. What that means is if we look at this HNMR diagram, it's of ethanol. And if we look at that, that diagram of ethanol, we will see the distinct hydrogen environments. So we have this hydrogen environment here, which is a hydrogen which is just bonded to an O. Then we have this hydrogen environment here. So both of these hydrogens are the same unique environment because they're both bonded to a C, and that C happens to be bonded to a C, and that happens to be bonded to an O. So they're both on the same unique hydrogen environment. Then the last one, it's 3 hydrogens sharing the same unique hydrogen environment, and that's because they're all hydrogens attached to a carbon that is attached to another carbon. So those are the 3 distinct unique hydrogen environments, and those correspond with the 3 peaks. Now, another thing that's important to remember with HNMR and also CNMR, which we'll get to later, is that the further to the left it is, so this OH, which is the furthest to the left, the further to the left it is, the more electronegative it is. So that OH is the most electronegative because of that O, because of that oxygen. The CH3 over here is the least electronegative because it's furthest away from that oxygen. So that's another important thing to look at when you're first looking at a HNMR diagram. So the 3 peaks means 3 hydrogen environments, and that one is the most electronegative. So once we figured that out, the next thing to do is look at the actual individual peaks. So this is splitting. Splitting occurs because of interference with the neighboring hydrogens. So you'll see that this hydrogen environment here, it has 3 neighbors, 3 neighboring hydrogens, and those neighbors will interfere with how this hydrogen is read. So basically what this means is if we look at the diagram, we'll see that the CH2, it has 4 mini peaks in the cluster. So there's 4 mini peaks here. Then in CH3 there is 1, 2, 3 mini peaks. And then here in the OH, it's a little bit hard to see, but it has 3 mini peaks. So you have the 2 small ones on the outside and the highest one in the middle. So the OH and the CH3 have 3 mini peaks, and then the CH2 has 4 mini peaks. So what happens in HNMR is the number of peaks in the cluster is 1 more than the number of hydrogens in the neighboring environments. So what that means is if we look at the CH2 here, it has 4 mini peaks. That means 4 is 1 more than the number of hydrogens in the neighboring environment. Yeah. So CH2, in the neighboring environment, we have 1, 2, 3 hydrogens. That is 1 more. That is 3. 1 more than 3 is 4, and that 4 is the 4 peaks. Does that make sense? So, like, there are 4 peaks, and in my head, 4 peaks means 3 gaps between. I like to count the gaps between. 3 gaps between means 3 neighboring hydrogens, which is 1, 2, 3. So that's that. Yeah, it's a little bit tricky to get your head around at first, but splitting is so important. Understanding splitting and understanding why it happens. First of all, I've seen a question in a past paper where they asked, why does splitting happen? It just happens because of interference from neighboring hydrogens. That's all you really have to say. But understanding splitting, why it happens, and how to read splitting can make all the difference in being able to determine what molecule it is. So for this one, let's say the let's look at the other splitting ones just to make it make more sense. So the CH3, 3 peaks, which means 2 gaps, which means CH3, there's 2 neighboring hydrogens. That's these 2, 1, 2, 2 neighboring hydrogens. Does that make sense? More sense, I guess. So yeah, you got the 2 gaps here, 1, 2 gaps in the cluster of 3 peaks, and then that corresponds with 2 neighboring hydrogens. So I'll give you more practice on this. We'll do a couple of practice questions in a sec. But here's another example. So there are 3 unique hydrogen environments because there are 3 peaks. We have this peak here, and this peak here. The most electronegative one is a singlet. So how we name them is a singlet for a single peak, doublet for 2 peaks, triplet for 3 peaks, and so on. So this one has no splitting. It's just 1 peak, not a cluster of small peaks, so this is a singlet. This one here, the least electronegative, has 3 mini peaks. So this one's a triplet, and so on. So there's no splitting, which means no neighboring hydrogens. So if we look at what the molecule is, which is here, which one has no neighboring hydrogen environments? Well, this one here has a neighboring hydrogen environment, which is this guy. And this guy has a neighboring hydrogen environment, which is this guy. So overall, this one has no neighboring hydrogen environments because it connects straight to an O, which connects straight to a C, and it has no hydrogens anywhere near there except for on that unique environment. So that singlet has to correspond with this group here. So hopefully that has made some sense, because splitting is a bit confusing, but as we do more practice, it'll make more sense. So now onto CNMR, which has no splitting, thank goodness. It's just an easier version of HNMR. And basically how we read this is instead of unique hydrogen environments, it's unique carbon environments. An important thing to remember, which I do think a lot of people get confused on, is just because it's a unique carbon environment, just because it's a unique carbon environment does not mean the number of unique environments corresponds to the number of carbon molecules. So sometimes you'll get a very symmetrical molecule. Let's take pentane, for example. Pentane has 5 carbons. So you've got 5 carbons just in a line, and that does not mean there are 5 unique carbon environments. There are actually only 3 unique carbon environments because it's symmetrical. You've got the 2 on the end, which are the same, 2, and then the 1 in the middle. So those are the 3 unique carbon environments of pentane. It's not 5. So sometimes the amount of unique carbon environments is less than the amount of carbon molecules. It's never going to be more. So it's read the same way as HNMR. The most left is the most electronegative, and it's electronegative because it's usually the most electronegative because it is bonded to an O or an N. So if we look at the diagram again, the most electronegative would be this carbon environment here. Then it would go here, and here, and then here. So those are our 4 unique carbon environments. The number of carbons in this molecule is the same as the number of unique carbon environments. So this is one of the ones where it's easy, but sometimes they like to trick you with symmetrical stuff. So just be careful with that. But yeah, so CNMR read the same way as HNMR, just no splitting, which makes it so easy to read. So just count the unique carbon environments by counting the number of peaks, and then go from there. So a practice time, it's a CNMR spectrum, and what gives rise to this spectrum. So if we look, you'll see there are 2 peaks, which means that there are 2 unique carbon environments. 2 unique carbon environments means that it cannot be, let's look. Okay, so if we have 1,2-dichloroethane, that is 1 unique carbon environment because it's symmetrical. If we look at D, 1,2-dichloropropane, this would be 3 different carbon environments. So that is also out of the question. If we look at chloroethane, you have the 2 C's, and then you have one of them with chloride on it, and the other one is just full of H's. That has 2 unique carbon environments, because one carbon has a Cl attached, and the other carbon just has 3 H's attached. So that's in the running. Then, if you have B, which is 1-chloropropane, you have 3 carbons, and one of them has a chloride on it, and then 2 hydrogens. One of them has 2 hydrogens on it, and one of them has 3 hydrogens on it. All of those are different, so those are 3 distinct carbon environments. So the only answer to this could be A, chloroethane. So the best way to approach these questions is drawing out all of the options and then going through them and cancelling it out. So if you draw all of them, you'll notice that only one of them has 2 unique carbon environments, and that's your answer. So yeah, just draw them out. That's the way to do organic chemistry. Just draw it a bunch of times and then you'll be able to figure it out. So that's CNMR. If we go back to UV Visspec, it's not directly mentioned in the syllabus, but you can also use it to determine some of the bonds. And you get a list on your data sheet, which is just there, and that kind of shows what wavelengths correspond with what bonds. The word chromophore could be a little bit confusing if you're seeing it for the first time in an exam, so just for context, it's a specific bond that produces a particular color, and you just use the formula sheet to figure out the answer. I have never come across a question where it has needed me to use that section of the formula sheet, but who knows, maybe this year will be the year they decide to chuck something in there like that. But yeah, you can just read it like how we read it before for that practice question with the concentrations. Very similar, except for this time you're paying more attention to what the wavelengths mean in terms of which bonds they correspond to. So I'll give you this other practice question, and we'll go through this in quite a bit of detail because this is what your HSC question would probably look like, or your trial question would probably look like. So here is the formula, C5H10O2. So immediately what you should be thinking about is whenever you see something that's O2, it could be one of two things. It could be a carboxylic acid, or it could be an ester. And based on the IR spectrum, we can figure out which one is which. So we'll get to that in a second. We have the formula C5H10O2, and then we have the HNMR, the CNMR, and the infrared spectrum. Before we look at HNMR and CNMR, we're going to look at the infrared spectrum, just because that can give us information on whether it's a carboxylic acid or an ester, and that'll make all the difference when we look at the HNMR and CNMR. So if we're looking at the IR spec, what we'll notice is that there's a really, really messy fingerprint region over here, except for this pretty distinct peak here that I'm pointing at. And this one, it's about 1,250. And if you look at your data sheet, this corresponds to a CO bond. So this still doesn't rule out whether it's a carboxylic acid or an ester, but it's something to keep in mind. The rest of the fingerprint region we can ignore. Then we can look at this here. So if you look at your data sheet, you'll see that if it's an acid, it would have a really, really broad peak around here. We are not getting that. We're not getting that broad peak at all. This is a very skinny peak. This corresponds to the CH bond. So we can rule out that it's a carboxylic acid, meaning that what we're looking for today is an ester. So another way to confirm this is this peak right here. This peak, if we read the wavelength, it's about 1750. This corresponds with the C-double-O bond. This is in an ester, just as the CO bond is, so it's an ester, almost certainly. And it is, like, it's not an acid, so it has to be an ester. After we figure that out, you should, the next step, I'm not going to do this right now in front of you, but you should draw out all ester options for C5H10O2, all the different combinations possible, and then we'll rule them out one by one. So if we look at the HNMR spectrum, it very, very, very kindly gives the splitting pattern, so I don't have to count it. So in the HNMR data, we have a doublet, a singlet, and a septet. So that's 7. So that's a lot. And the most chemically shifted, so the most electronegative one, is 7 neighboring hydrogens. So that suggests that it has an environment on one side, an environment on the other side. It's not just one of those ones that's just one environment on one side. and then the oxygen. So that can already give us some information on what is happening here. Then for the CNMR spectrum, you'll see that there are 4 unique carbon environments. So CNMR has 4 unique carbon environments, HNMR has 3 unique hydrogen environments. Now, I'm not going to go through the entire process here. It's really just checking whether that splitting counts, but what I will do is, this is the answer. So I'll explain which parts of the molecule go with which sets of the data. So obviously it's an ester. I'm not going to name it because naming esters is confusing. Anyway, so we have this. Basically, if we look at the CNMR spectrum first, we'll see that there are 4, and here we can count 4 unique carbon environments. So first we have this one. This one is just a C that's connected to another C that's connected to 2 O's. So that's 1. This is another unique carbon environment here. This, pretty self-explanatory, another unique carbon environment. This here is another unique carbon environment. And these 2 are the same carbon environment. If we think of the symmetry, it doesn't look like it's the same one here, but if this was written on top here, then you'll see that they're the exact same carbon environment. They're the exact same carbon environment. So that's something to remember there. Now, if we look at the most chemically shifted hydrogen, the most chemically shifted hydrogen would be this hydrogen here. That hydrogen in there is connected to a carbon that's connected to an oxygen, and then another oxygen here. So it'll be the most chemically shifted. And we can see that that hydrogen has 2 neighbors, and those neighbors have 3 hydrogens each. So that's 6 hydrogen neighbors in total. Those 6 hydrogen neighbors, if you add 1, that's 7, which means there should be a septet. And that's exactly what we have as our most chemically shifted. So there's 7 peaks at the most chemically shifted cluster, and that means 6 neighbors, and that's what this hydrogen environment has. 6 neighbors for the 7 peaks. It's a little bit confusing, I know, but the number of peaks is 1 more than the number of neighbors. So the number of peaks, 7, is 1 more than the number of neighbors, 6. Sorry if that kind of confused you, but just remember, number of peaks, 1 more than number of neighbors. Okay, so if we go to the next most chemically shifted, it's a singlet, which means there are no neighbors, and that means it's this one here. This one has no neighbors whatsoever, because it's connected to a carbon that has no hydrogens on it, connected to an oxygen. There's no neighbors for this one. And it's the next most chemically shifted because it's closer to the oxygens than these ones are. Then, our last hydrogen environment, these ones here. So these two groups have the same unique hydrogen environment, again because of the symmetry. And these 2 have 1 neighbor, 1 shared neighbor, and it's this single hydrogen. One hydrogen neighbor means that there should be 2 peaks, and there are, because it's a doublet. So that's the reasoning, and basically that's what you need to do in the HSC. So you basically just use the information, write all the possible ones down, and then just cross them off. Process of elimination is the best way to do it. Just go through all of the options and then find one that fits everything exactly. If something doesn't fit exactly, it's not correct. Because that's something that I did. I found an option that fit kind of like 50%, I'd say 80%. It fit everything but one section of the splitting. And I was like, oh, surely it was just a mistake on my end with counting the splitting. Surely this is right. But no, it was wrong. I put the barium in the wrong spot, or the chloride or something like that in the wrong spot. So it was completely wrong. But yeah, it's just really important to be careful with the splitting, because that tells you exactly where everything is. So that brings us to the next part of this, which is the final inquiry question, chemical synthesis and design. So chemical synthesis and design, it's a very small little inquiry question. What are the implications for society of chemical synthesis and design? But it's a very strange inquiry question, and I will go through why. It's because it's basically evaluating, and it's very difficult to think of questions for this, example practice questions for this. I got one in my HSC that was kind of a curveball, but I'll go through that later. Basically, the factors that you need to consider are availability of reagents, reaction conditions, yield and purity, industrial uses, environmental, social, and economic issues. And things to keep in the back of your mind when you're going through chemical synthesis and design is Le Chatelier's principle, which is important because when we talk about yield and reaction conditions, this is key to figuring out what gives you the highest yield and what best reaction conditions are they. And then necessary reaction conditions for organic reactions. For example, if you need catalysts, if you need it to be in the presence of, let's say, acidified permanganate, reflux conditions, all of that kind of stuff. Like if there needs to be dilute sulfuric acid, things like that, you need to know. And then monitoring and managing chemical reactions. So this goes back to our monitoring the waterways and all that kind of thing. If it produces toxic waste, so let's say that the industrial process that you're doing ends up in the formation of carbon monoxide that you'll just release into the atmosphere, is that the best synthesis chemical design? Probably not. So you need to find ways to use up those toxic chemicals or prevent them from being just released out into who knows where. So we'll go through each of these factors individually. The overarching, I guess, process that you should think about when doing this part of the syllabus is the Haber process, or the Haber-Bosch process. So that's the equation for it. Know that equation off by heart. Know that it's exothermic, and know that it requires an ion catalyst, and that the best reaction conditions for it are low temperature, high pressure. And basically, all you need to know is that ammonia has lots of uses, particularly with fertilizer, and it's been used as a fertilizer for a very long time, especially in producing food during the First World War. And yeah, so if you know that it's exothermic, ion catalyst, low temperature, high pressure, know the equation, know that it can be used as a fertilizer, and that's it. That's all you need to know about the Haber process, and you'll be able to evaluate it. So first factor that it said to go through was the availability of reagents, and this is important, and it also ties into environmental factors. I'll get to that in a second, but it's important to figure out where your reaction will be located because of how available the reagents that you need for the reaction are. So you don't want to be doing your reaction in a factory that is in a different country to wherever the reagents are, because then you'll have to spend money on importing those reagents, and spending that money is not good economically for your chemical synthesis design. Then on top of that, transporting it will be horrible for the environment. Think truckloads of whatever you're transporting, all that emissions. Like, there's so many things that could be reduced, your environmental impact and your economic costs. All of that can be reduced by choosing a reaction and a reagent that are close together. So keep that in mind. An example is polyethylene from ethylene. It can be sourced from biomass and fossil fuel sources. And obviously, this will depend on location and availability, so choosing a place where you'll have that availability is important. And in ammonia, nitric acid used to be used to get nitrogen, so they went through another chemical reaction to produce nitrogen from nitric acid, and in doing this they could make ammonia through the Haber process. But the important thing was that that first reaction to get nitrogen was something that you would evaluate when you talk about the availability of reagents, because it wasn't the reagent, nitrogen was not readily available. You'd have to do other processes, which would cost money, cost time, all that stuff. So something to keep in mind. Next thing is reaction conditions and yield. So it's important to consider what reaction conditions will cause the best yield, and also the best reaction rate, because you want it to go fast. So you'll often think of this with collision theory and Le Chatelier's principles. So ammonia production through the Haber process is exothermic, and when it's exothermic, it means that it works best in terms of yield at lower temperatures. So that lower temperature is not good in terms of reaction rate. That means the rate of reaction will be quite slow. So you have to compromise between wanting that great yield but also wanting the fast reaction rate. Then, basically, another thing to consider is that high pressure, which is favored for the Haber process in Le Chatelier's principles, that is super important to consider, because high pressure is expensive. High pressure is so expensive. So you don't want to be spending that money. You want to make a compromise, and that's why the overall reaction conditions are 400 degrees Celsius and 100 newtons. I mean, not 100 newtons. 100 MPa. Why do I not know what that means? 100 MPa, yeah. And another thing to consider is if it requires a catalyst. The Haber process requires an ion catalyst, so that would increase the reaction rate, drive it forward. Another thing is that during the Haber process, what happens is the gas ammonia that is produced is changed into a liquid and collected as a liquid basically immediately. And then once it does this, it's removed. And once it's removed from the system, this will cause Le Chatelier's principle to work. And when it does this, once it works, it'll basically just like shift right to produce more yield. So Le Chatelier's principle is really important. It just helps you figure out what reaction conditions are best to produce the best yield. Okay, so the next thing is yield and purity. So the quality of reagents, and also whether or not another product is made in the process. If another product is made, it's important that you find a way to remove that so that it still has high purity. For example, when synthesizing something by a hydration reaction, there are other products. So we want to make sure that those products do not affect the yield or purity, that you get rid of those products in some way, shape, or form. Another thing is with the Haber process specifically, gas molecules are filtered to remove contaminants which may damage the catalyst, and this may decrease the purity. So all things to consider while going through and evaluating chemical synthesis. Another thing is industrial uses. Basically, if there's no use for whatever you're synthesizing, it's not worth making it. So another thing is if it requires high purity, then you'll need to consider if the industrial use requires higher purity, then you will need to consider different reaction conditions than if it requires lower purity. So cheaper soap would obviously be less pure than more expensive soap. So you would use a different process in chemical synthesis for those things. So as spoken about earlier, ammonia is used for fertilizers, and it's used in lots of fertilizers. It's very good for fertilizing, and it was really needed in the time of World War One because they needed lots of like food, I guess. So in the context of the harbour process in World War One, ammonia was used as a fertilizer a lot to make sure they had enough food. And the harbour process is thereby driven to be as economical and widespread as possible, because during the war, obviously they're spending so much money on the war and on the fighting, they don't have money to spare on making sure that they could have a very, very expensive synthesis. They needed a cheap synthesis design, if that makes sense. They needed it to be cheap. So that's why you need to consider the industrial uses, because yeah, like it's pretty self-explanatory. They wanted it to be economically viable in that kind of time period, and therefore it occurs at a lower pressure even though it might not provide the best yield. And that's because also with the industrial uses, it's being used as fertilizer. Like, the purity doesn't matter too much because it's fertilizer, and at the time it didn't matter too much because they really just wanted fertilizer to be able to just grow food for the soldiers. Like, they weren't really picky about that kind of stuff. So that's just something that you need to consider. Next is environmental, social, and economic factors. So yeah, this kind of ties in with everything else, like I said, about the cost of transporting it if your reagents aren't available in a close by area. Also, like the emissions of transportation and social concerns, animal welfare, all those kinds of things. It's pretty self-explanatory. It's just you need to make sure that you're not harming the environment. Let's go back to my example of carbon monoxide. If your synthesis process requires you to release a ton of carbon monoxide into the environment, you're not only killing the atmosphere, you can also have very substantial impacts on animal life and human life. And so, is that really ethical? That's something that you have to ask yourself when doing chemical synthesis and design. You don't want to be producing toxic waste. You want to be able to remove that and be able to use it for something else. So what made the harbour process successful was that it used less power, less complex equipment, cheaper reagents. It was so much better than other nitrogen fixing processes, and in the context of the war, it was so useful as well. And on top of that, it's like the economic part is really important in the war. As a modern history student, this is very like what I used to talk about. But anyway, main thing is consider the environmental, social, and economic factors. There's really not much I can say about it, because when you get a question about this in the HSC, it's going to be something like the question I got in the HSC, which we'll go through in a second. It's never going to be something super specific. It will be evaluating, and you just need to know things like Le Chatelier's principles, what environmental, social, economic factors means, what availability of reagents means. You just need to know what it means, and then we'll get to the evaluation stuff in a second. So, okay, we'll get to the evaluation stuff in a second. It's coming up in the PowerPoint. First, we'll do these revision questions for 8.2. So this is a HNMR diagram. It has 4 clusters. Those 4 clusters means 4 unique hydrogen environments. If you look at the drawings for the 4 molecules on the side, you'll see that there are, most of them have more than 4 hydrogen environments. So if we look at A, this is a hydrogen environment, this is a hydrogen environment, this one is one, this one is one, and this one is one. So that's 5 unique hydrogen environments. That's more than 4. If we look here, this is a unique one, 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 and this is a unique one. That is 1, 2, 3, 4, 5. That is 5. That is more than 4. If we look at C, these two are the same. This is the same. So that's 1, that's 2, that's 3, and that's 4. So therefore we have 4 unique hydrogen environments. And that means that C is what we're looking at here for the HNMR. If we look at this, which is a CNMR diagram, you have your, again, 2 unique carbon environments. And which of these has 2 unique carbon environments? So we start at the top. This has 3 unique carbon environments. This one here, and this one here. This one has 2 unique carbon environments. Let's keep that in mind, because maybe there's another one with 2 unique carbon environments. C has 1 unique carbon environment, because this is symmetrical. This is the same. And same with D. So B is our answer here. Okay? Now, this is revision for naming the unknown compound. This is a past HSC question. Basically, if we look at this, we ignore the fingerprint region. First, we should look at mass spec. We'll see that the molar mass is 86, and we should keep that in mind. Then we'll figure out how many carbons there are based on that. Then we've got the infrared spectrum. If we look, you'll see that there is a C double O bond and a CH bond. This could mean multiple things. An aldehyde or a ketone. Could be either. But we'll see. Then if we look at the proton and carbon NMR spectrum, see that there are 3 unique hydrogen environments and there are 4 unique carbon environments. So this already tells us something. This tells us that there's some sort of symmetry happening. There is a hydrogen environment where there's like 2 that share that same unique kind of organization, because there are 4 carbon environments and 3 hydrogen environments. Anyway, basically how this works is if you look at the mass spec, you'll see that it's 86. That mass of 86, if we say that it's a ketone or an aldehyde, that means that there are 5 carbons. Okay? There are 5 carbons, so those 5 carbons, we move on to figure out, well, is it just straight up pentanone? No, it is not, because of the splitting pattern that it shows and the carbon NMR. So that means that there's a methyl branch somewhere, because there are 4 carbon environments and 5 carbons in the molecule, so there has to be a methyl branch somewhere. And basically, you look at the proton NMR, you have one most chemically shifted, which has 6 neighbors. You have one that's the next chemically shifted, it has no neighbors. And then there is a doublet at the end, 1 neighbor. So all of this really comes down to, oh, I didn't have the answer up, but I will tell you the answer. It's 3-methyl-butane-2-one. So if you draw that out, you'll see that it all works out to be like corresponding to these what are they called? Diagram. You'll see that it all works out to correspond with these diagrams. But again, how you approach these is just draw it up and then it will make sense. Now, back to the chemical synthesis thing. This was from the 2022 HSC, and I did panic when I saw it because it was 8 marks for something that I did not spend that much time on. So basically, analyze how a student could design a chemical synthesis process to be undertaken in the school lab and then relate it to an organic compound with a chemical equation and refer to these things. So I chose esterification because I knew those reaction conditions really well. So I could easily talk about the reflux conditions, the sulfuric acid that was needed, also that heat was needed. You do it on the in heat. It needs to be heated up because it needs to be vaporized, I guess. Anyway, so reaction conditions for esterification were quite clear, and you should know that from organic chemistry. Then selection of reagents, it's pretty easy. You have a carboxylic acid and an alcohol. Those are very ready in a school lab kind of setting. It's not something that's too hard to obtain for schools. Then potential hazards, you have the fact that you're dealing with hot stuff. So I could talk about that. You talk about how if you don't cool down the alcohol that's getting vaporized, inhaling alcohol might be bad. You should open up the windows, do it in a fume hood, those kinds of things. Also, if the gas gets out, it could be volatile. I mean, it is volatile. Gas gets out, it could be flammable. You don't want it to be near an open flame. All that kind of stuff. Basic school lab rules. You can just talk about there. So that's just what I did. And then yield and purity of the products. You can evaluate this and analyze this by saying things like, how do I know that the end product is all ester and not some runaway alcohol that was just volatile and ended up being put with the end product? So it's like there was quite a bit to talk about for that. But when you get a tricky question like this, a sort of curveball, if you will, you just need to go with what you know. So don't try to find it. Asks for an organic compound for a reason. It's because there's not many options when you have to talk about the synthesis of an organic compound. There's not many options in a school setting. They're kind of giving you a hint that you should probably be doing esterification. And esterification, if you know the reaction conditions, you're good. Like the fact that the ester is removed and it causes like Le Chatelier's principles to favor the formation of the ester as more of it is being made and being turned back into liquid form. All of that stuff, it's all good things to talk about. Getting to 8 marks, I don't actually know if I got, like I could have gotten a 4 out of 8 on this question. I don't know. I didn't get my paper back. But from what I read in the marking criteria, I did answer the question. So hopefully I did well on that question. But yeah, 8 marks worth. Make sure that you put in the chemical equation because it asks for it. That's like 100% a mark. And don't forget to add in your states because that's very important as well. But yeah, this is the type of question you get for chemical synthesis and design, and it's a weird one. It's really weird. So just keep in mind that chemical synthesis and design is a very weird question, and like it's a very weird part of the syllabus, and you'll get weird questions on it. So you just need to be prepared to analyze the information that they give you on the day. Like you can't really prepare for it other than knowing your Haber process and knowing its reaction conditions, because if they ask you to provide an example, Haber process is probably the best way to go. So that's all the content for Module 8. Now for revision and just advice. Module 8 is big. It is confusing at first. It is a lot to take in, and the main things that you should be able to do in order to succeed in Module 8 really is just be able to read those HNMR, those CNMR, mass spec, and IR spec diagrams, make sure you know how to read them well, because again, I can almost guarantee that that will be in a trial or the HSC. Then know all the factors of the chemical synthesis process, be able to name them and be able to say something about them and know what they mean. By being able to say something about them, knowing how they are in relation to the Harvard process, it makes it really easy to think of something on the day if you're given like a curveball kind of question, like how I was in the HSC. Then also knowing your solubility rules and flame test colors and even precipitate colors. But yeah, that's really all there is to it. It's a lot of memorization at the beginning, memorizing your process, memorizing those solubility rules and all of that. But in the end, it just ends up being a skills thing. It should come almost automatically to be able to just go, oh yeah, this is soluble, this is insoluble, and this is like 43 is a propyl fragment, 29 is an ethyl fragment. All that kind of stuff gets easier the more practice you do. So that's my thing for today. Like, you're not going to get it straight away. It takes a lot of practice. It took me a lot of practice, and I still get confused sometimes. So all you need to do is just try your hardest, and you'll be fine. So how to approach tricky questions when it's in an exam situation. Your first instinct is always to panic, but don't panic. That's silly. Well, it's not silly, it's natural. But if you panic, you're wasting energy on panicking when you could be using that energy to being able to get as many marks as possible. So when you're panicked, you see a question, you have never seen anything like it before, you don't know what's happening. Instead of giving up, you should think, how can I get as many marks as possible on something I have no clue what I'm doing? So how you do that is first write a balanced chemical equation. That's always 1 mark. They'll always give you a mark from that, almost always. And if not a balanced chemical equation, if it's like module 5, write your KEQ or your Q or your KA. Write the formula for that down. If you're having something to do with mod 5 or equilibrium in general, just do a rice table. They love rice tables. It shows that you tried, and they'll probably give you some marks for some like relevant working out or just like trying working out. Like, so the markers aren't there to make you feel bad about yourself. They're there to give you as many marks as possible if they can. So just write something down. Don't leave anything blank. That's a waste. If you are a little bit confused, you can ask yourself these questions. So you need to ask yourself, what information am I given? What am I trying to find out? So if you're trying to find out moles or mass, you'll do 2 very different approaches. Well, not really. You'd find out moles first and then just convert it to mass. But you need to remember like what you're doing, what the goal is. And then another easy thing to do is figure out what module it's from or what topic it's from. So if you see that equilibrium sign, you know it's equilibrium. You know that it's probably a rice table. So you draw a rice table. And if it's not equilibrium and it doesn't look like it's organic chemistry and it's not acids and bases, it's probably some weird part of module 8 or some weird cross-module question. Really, when you're in that situation, just find the moles of stuff. That was a trick that I used. I just found the moles of everything, the moles of whatever they gave me, and then I would just write it down. And then if it didn't come to me then how to do the question, I'd just leave it all there and I would get some marks still because they were happy that I found the moles of something. So relevant working is a word that they use in the HSC marking, and that is a very broad term, and you can easily get marks for relevant working. So you should always try to do that. So some overall advice about the HSC is, first of all, that burnout is so real. It's still real, and you should not let it ruin high school. Because, you know, the HSC, it's fine, but there's other stuff that's going to happen in your life. Like, don't let it ruin high school. That's so sad. That's just, don't let that happen. But yeah, do stuff that you enjoy, or better yet, plan something cool to do after the HSC so that you have something to look forward to. I went to Queensland, so that was fun. I was looking forward to that all throughout my HSC. And yeah, that's basically it. Don't stress out too much. Find a way to de-stress. It's different for everyone. Just don't make the HSC ruin your life, basically, because it's not that serious. Well, it is serious, but it's not that serious. If getting into uni is stressing you out, from someone who didn't get their first preference, know that there are so many pathways. Like, you can go so many different ways to get to one spot. Like, let's say, let's do a little, like, analogy, a little example. If there's a road closure and you're trying to get home and there's a road closure, you don't just give up going home because the road is closed. You just go on a detour and you go a longer way. So you still get home. You just do it some way you wouldn't usually do it. It's like that. You'll get there eventually. It just might take longer. Anyway, that was a side note. Yeah, so basically, if you don't know by now what study methods work best for you, then that's something you should try do. Try find the best study methods for you. Active recall is more important than any note taking you'll ever do. So practice questions, flashcards, anything like that. That'll help you so much more than just writing a bunch of pretty notes. Another thing is fix your sleep schedule. Sleep is so important. And also, if you get a bad mark in your trial, know that it's because trials are on purpose really hard. They're trying to mess with you in trials, because it's better that you make mistakes in trials than if you make mistakes in the HSC. So if you get a bad trial mark, or just a trial mark you wish you did better on, just learn from your mistakes, move on. There's nothing you can do, really. Just catalog where you made those mistakes, take note of them, and then just do your very best to make sure that those mistakes never happen again. So in my trial, I found out that I'm really bad at rice tables, and then I got really good at rice tables for the HSC because I didn't want to mess them up again. So yeah, we'll do a quick practice of the other modules now, and then we'll be done. So for this is module 7, and it's name the following compounds. So A, we have a carbon-carbon double bond, and we have a random F. So we deal with the F second to the carbon-carbon double bond. So we say that it's without the F. If it was no F there, we'd have prop-1-ene. And because the F is on the third carbon, we have 3-fluoro-prop-1-ene. For B, we have multiple functional groups one. Multiple functional groups is kind of hard because you need to remember which functional group takes priority. How I remember which one takes priority is that the ones that have the higher masses are usually the ones that take the most priority. So this is an alcohol and a carboxylic acid. The carboxylic acid takes priority, so it'll be propanolic acid. There is a hydroxyl group on the third carbon, so it's 3-hydroxypropanolic acid. Pretty self-explanatory there. So this one is reaction pathways. So we're starting off with unsaturated molecule, and we need to get ourselves to that carboxylic acid hydroxyl group situation. So how we do that is we need to first make it into an alcohol, which can then be oxidized into a carboxylic acid, and then from there we can change it into the extra hydroxyl group. So how you do that is we'd start off with substitution, so that F would become an OH if we add sodium hydroxide. Then what you do then is, now that you have an alcohol, basically, what you need to do is oxidize it. So you get your acidified permanganate and you oxidize it, so then you'd get an alcohol. I mean, you oxidize it, so you go from an alcohol to a carboxylic acid. And then once that's done, you want to get rid of that carbon-carbon double bond. So once you get rid of that carbon-carbon double bond, how you do that is hydration. Hydration, it'll split it up, so one gets an OH, one gets an H, and that will end up with your final product. So reaction pathways, you just go through all the different organic reactions. You just need to know your organic reactions, and then you'll be all set for reaction pathways. So for this, they can both be turned into polymers. What type of polymer could each become? So the carbon-carbon double bond is a very good sign. That sign tells us that it will be an addition polymer, and the OH over there and the H, like the H and the OH, these guys, I'd say, this one here and this here, they are signs of a condensation polymer because they would come and form water, and that's a condensation polymer. So there's your answer. A is addition, B is condensation. So if we're going to module 6, let's consider compound B. It's an organic acid. What does it mean in terms of Bronsted-Lowry theory? So a Bronsted-Lowry acid, that is a proton donor. And a proton donor, it will donate a proton. That's basically all you would need to say for this type of question. It donates this one here, or this one here. Yeah, that's basically it for that question. This one is a little bit tricky. It's your Ka, pKa stuff. So the relationship between pKa and Ka is the exact same as pH and H. So keep that in mind. But given that a compound B has a pKa of 4.5, determine the pH of 0.1 molar solution of compound B. Here is the solution. So first thing I did was write out an equation, and I just assumed that it was a monoprotic acid for this. Then what you do is you use the pKa to find the Ka. Then you write an expression for Ka based on the equation. So again, some extra marks will be given for that Ka if you have nothing else to offer to answer the question. If you have no idea what to do, write that Ka expression down and it will help you out. Then just some normal algebra, and then you get your pH. So that's that. Yeah. Then this is a mod 5 question. So this question is, it's in a sealed rigid container, which means that it's a closed system. So equilibrium can be established. And what will happen if the temperature was increased? So it's exothermic, which means that an increase in temperature will drive the reaction left, which means that the amount of NO will decrease. So this is all just Le Chatelier's principles, basically. Here is another one that's Le Chatelier's principles. This is account for changes in the conditions that have shaped the graph during the time the system was observed, include a relevant chemical equation. Basically, for this, we have a concentration of, at T1, we have the concentration of N2 increase. That means that N2 was added because none of the other ones are doing anything. So nitrogen was added. Also, something else to consider here is that this represents the Haber process. Just a fun thing. Anyway, at T1, N2 was added. At T2, all of them do a quick little increase. So that means that the pressure increased. And that means that the volume decreased. So that's what you would write there. And for T3, it all has no like sharp spikes or anything, but they all do a little curve. And when you see that, you should know immediately that it's a change in temperature, because if it was a change in pressure, it would be a spike of some sort. If it was something being added or taken out, it would be only one of them spiking or not spiking. When all of them are moving in that curved shape, it's a change in temperature. So in this case, we know that the Haber process is exothermic. So if the product is decreasing, so if NH3, ammonia, is decreasing, that means that the temperature must have increased. So that is all the info that I have today. It was a lot because Module 8 is a lot, but I hope that you learned something of note here, or maybe even just started to understand something that your teacher couldn't explain to you. Yeah, so hopefully real-time Isabel has been answering your questions on the side. But yeah, thanks for coming and listening in. I had a great time. Yeah, cool. I hope you guys do a great job in chemistry, because chemistry is hard. Don't give up, because chemistry ends up being a little bit fun, especially in Mod 8. So yeah, good luck in chemistry. Bye.